Hi, this is Mark McDonald. I'm going to present to you my final project called Pathfinder for CSCI E89 Deep Learning class at Harvard Extension School, Spring 2019. Robots have advanced in recent past to be able to navigate quite well through off-road environments. No longer are robots prescribed to environments that have flat surfaces that they can roll over or prescribed type of pre-identified obstacles. These robots can move over rocks and up and down stairs quite easily and often much better than humans can do. What the Pathfinder project aims to do is to provide these ground-based autonomous vehicles and robots support with understanding the environment they're in so that they can choose a path that is safe for them to navigate. Here are some pictures from Boston Dynamics of their robots that have been quite impressive in navigating challenging landscapes. I encourage you to search these on YouTube and watch them. They're quite fascinating. I'm going to be using a Mac with an external GPU. Had some problems in that Mac Mojave no longer supports NVIDIA external GPUs. However, TensorFlow only works with an NVIDIA GPU. I switched to using a Plaid ML backend for Keras so that I can use a GPU with my Mac. I tried to limit the number of libraries to Keras, OpenCV, and SciPy. I generally don't like to use a lot of third-party libraries in a lot of my work. And the model that I ended up using is a convolutional autoencoder where we encode images and decode the image into a mask. The data that we'll be using comes from the project linked to at the top of the slide here. It's 7 gigabytes of data, which is quite extensive. It's composed of MAT files, which are basically dictionaries of data. The data represents 6 training videos and 3 testing videos. They're pretty short, but effective. The training videos have both a video or an image and a mask, where the testing data only has an image. My program relies on a master Jupyter notebook and uses 3 support Python scripts to keep the amount of code in the notebook down. The process asks the user to create 2 directories to move the downloaded data into. One of the directories is for the test data and one is for the train data. The master notebook script will ask for a path to these directories, and the remaining directories are automatically created. This is what the directory structure will look like. The user-created directory names can be anything. You'll notice that in the selected directory here of training data, you see a series of MAT files. Each MAT file represents a frame in a video sequence. Each file, as I mentioned, is a dictionary that contains data elements. 2 of those data elements will be relevant to this project. One of them holds the array that represents the image, and the other holds an array that represents the mask. What we do is we will overlay the mask onto the image to create a superimposed image. After we create a model, we'll use the test data to create a mask from our model and overlay that onto the image. The script will create a short video with the manual overlay. I'll show a demonstration in a moment. The code highlights some of the challenges here. Small data set required the use of data generators. This was a problem with the image and the mask needing to both be augmented identically. We solved that. The other challenge was kind of finding the right augmentation characteristics to use. I found that using augmentation that required any fill areas didn't work well. So that kind of limited the amount of augmentation styles that could be used. I use a technique in the script where the master notebook requests a model from one of the supporting scripts. And when it gets the model, it also gets a dictionary object that holds a description of the model, including all of the parameters that the model will be trained with. This makes sure that my data generators are perfectly aligned with my model, and it gives me the ability to save that variable later so that I can recreate or revisit what settings were in that model. I use a function that's defined in one of the support scripts to get a model. This defines the convolutional model that we defined with all of the parameters that you can choose to train it with. I generally have it set so that it will default, if no variables are input here on the get model function, the most optimal parameters are chosen. These are optional parameters and don't need to be set. This is what the dictionary object looks like. It's basically what you would expect, key value structure of the parameters from the model and their values. This particular dictionary object is extracted from a trained model, and you'll see at the bottom that before we save it as a pickle file, we'll also include the history and the results. I went through various different parameter configurations. I first tried a Reuters-like approach where we had a multi-class classification. My idea was that I would make masks 30 by 40 images, 1200 of 1200 elements. Each one would be considered a class, and we would use kind of the Reuters-like process to determine if those pixels should be classified or not. It kind of worked, but it could only get good to a certain point. There's nothing I could do to make it better after the first basic setup. I then decided to try using a convolutional autoencoder, which proved much more flexible. Basically, the idea is that we'll encode an image and decode it back into a mask. I tried making the encoding with several different sizes, ranging from 1200 to 9600. I found 2400 to be the best, which I thought was pretty large, but it was effective. Nonetheless, this might be something worth tweaking in subsequent efforts. I found that color was the best, probably because some obstacles are identified by color. I found ReLU as the final activation to be the best. I found no regularization to work the best, and somewhere between 30 and 40 epochs were best. Any more, I tried training it overnight with hundreds of epochs, and it just ruined it. It just didn't work at all. Anything less than 20 doesn't work either. So there's a fine range there in which this works well. So we'll go through the small demonstration. Step one is I set the back end to Plaid ML to support my AMD eGPU. This can be commented out if you don't have a GPU or if you're using an NVIDIA GPU card. Then in the subsequent step, we kind of check, in the subsequent steps, we check to make sure that we're in the right directory. We create the directories that are necessary for the program. We set variables to the directories that were created by the user that contain the downloaded data. Finally, what we do is we extract all of the images and masks from the test data and put them into the directories that the program creates. This is what the directory structure will look like after everything is set up. You see that the directories at the bottom are created automatically. They must be in that format in order for the scripts to work. And I'll show a little demonstration. What we do is we create overlaid videos from our test data just to show what masks look like over the video sequences. Here we see a nice clean mask that overlays a short video scene. We'll also notice that there's actually 3 levels of masking. There's a path, there's an obstacle, and then there's a little red ambiguous area. This proved to be too much data. So what I did is I changed the masks in step 6 here. On the left you see a mask that includes 0, 1s, and 2s for paths, ambiguous, and obstacle data. And we change it programmatically so that the paths are identified with a 1 and obstacles are identified with a 0. This speeds up training and improves the output dramatically. So we do a training demonstration. Here I'll show an example of what the final output looks like. Here you notice that we get a model to train from one of our support structures. The variables that are provided here provide a nice simple way to make sure that, or to help with creating a model and a generator that will be aligned with one another. Using this approach also helped me to define several different parameters for several different models and train them all sequentially in an unattended manner. In this example here, we're only defining one model, but we could have several lines, each of which define a model that follow this, and then run the training script and get video output for all of them. So training, I'll show a training example here. The training can take somewhere between 15 and 40 minutes, maybe an hour, depending on if you're using a GPU, the settings, and the settings. As I mentioned, more than 40 epochs deteriorate the results. The script will give you a little bit of information about the training results, and the script will also automatically create an output video in a directory, in the results directory that the program creates, that has a unique directory name. The output will, in that directory, there'll be a pickle file that includes the trained Keras model and the description, and it will also include this video, which also has a little overlay of the what will be the directory that it's in. So we'll start this video. It includes 3 sequential scenes that are extensions of the training scenes. The first one here is of harsh lighting conditions. Now, this isn't working so well. This is the very challenging environment, much more challenging than what was trained on. But you can see the sky is not highlighted. Some of the hay bales are not highlighted as navigable paths. And as we go around the corner here, we see it's identifying the path in front of us, and it's avoiding some of these hay bales here. We narrow the bend as to what I consider probably the most challenging of all the clips or parts of the clip that we have here. The tree on the right is highlighted. That is clearly an obstacle. But here we're seeing like it's generally giving you the area that can be navigated. Here, less harsh, same area, less harsh lighting conditions, overcast. Here, where I paused, we see the hay bale is clear right in front of us, is clearly not highlighted. And as we go around the corner, similar results as with the harsh lighting conditions, a little better, but here we can see clearly that it's not highlighting the areas to the left. the tree's still highlighted, but under the tree is navigable so that could be possible. It's clearly not a random blob. In the third sequential clip of our test is the most easy to navigate environment, where we have bushes and trees to the left and the right. Here we can see that our navigable blob of slime is clearly marking the path. Here it has a tendency to move to the right, and it's highlighting this area with the poles as navigable. It is a path, it just has a couple poles in the way. As our video turns to the left, it gives up on that because it's not there, and it focuses on the path ahead. This is working perfectly. It's very clear that this is not random. It is following a prescribed path right to where it should go, up to the very end. Even here we notice that there's a little path to the right, and it is already identifying that path as a potential path. And that is the end of the clip. So I think we found a method that works. I think that we could probably train this better and make better settings. We could probably train define the model so that it might have more layers, might hold more data. I found that coming up with the best parameters was a trial and error effort. I tried to do this mathematically, but it didn't really work. Sometimes it just was impossible to determine which set of parameters was going to work better than others. That was a big takeaway for me on this project. Also, the number of parameters is quite overwhelming, and then sometimes I just accidentally stumbled on things that worked. I think that, like, if I was to work on this a little further, I would clearly explore different model designs. The program is set up so that that's relatively easy to do, and it clearly supports that. I like the autoencoder process. I think that it's the most effective. I think that for the application that works the best. If you can encode the image, then you could use different decoders based on different objectives that your vehicle or robot may have. So for example, if it's on a search and rescue mission, it can encode it with a basic encoder, but the decoder maybe not only is looking for a path, but it's also looking for a person. If your robot is picking mushrooms in the forest, you can create a decoder that will identify edible mushrooms that it should pick. Clearly, if it was doing something else, you wouldn't want to waste the effort on processing power to identify if mushrooms are edible or not. I think we're on the right path. I like the model. I like the structure. I feel that it's pretty successful, and I thank you for your time in listening to me. Thanks.